Hello everyone, I'm George Božić from MDPI and I'll be your host for today. Welcome to the webinar, Advances in Acoustic Emission Technique, Test Interpretation and Numerical Simulations, organized by MDPI and the Journal Applied Sciences. Before introducing the MDPI, Journal Applied Sciences, and the lineup of today's event, I would like to remind everyone that this webinar is being recorded and the recording will be made available as soon as possible on a webinar webpage. Please note that you need to be logged into the site forum in order to see recordings.
Okay.
A pioneer in scholarly open access publishing, MDPI has supported academic communities since 1996. Based in Basel, Switzerland, MDPI has the mission to foster open scientific exchange in all forms across all disciplines. Our 469 diverse and open access journals, including 460 peer-reviewed open access journals and 9 conference journals, are supported by more than 295,000 academic experts who share our mission, values, and commitment to providing high-quality service for our authors. Applied Sciences is an international peer-reviewed open access journal on all aspects of applied natural sciences, published semi-monthly online on MDPI. There will be 3 presentations today of 20 minutes each. The presentations are followed by questions and answer sessions moderated by webinar's chair. Our journal has relevant special issue related to the topic of this webinar, titled Advances in Acoustic Emission Technique, Test Interpretation and Numerical Simulations, guest-edited by Professor Lacidonia and Professor Itorius, our chairs. Deadline for manuscript submissions is 31st December 2025. If you have any questions for speakers, please feel free to post them at any time in the Q&A box. You can find it in the Zoom menu bar at the bottom of your screen. It would be great if you could use the Q&A option and not the chat panel for the questions to the speakers. Today's webinar is chaired by Professor Giuseppe Lacidonia from Politecnico di Torino from Italy, and Professor Ignacio Itorius from Federal University of Rio Grande do Sul. Professor Lacidonia and Professor Itorius, thank you so much for chairing this webinar. That's it from me. I'll now hand over the floor to you and enjoy everyone.
Thank you very much for the introduction, Georgie. Well, good morning and afternoon, everyone. It is a great pleasure to introduce today as Applied Science webinar, Advance in Acoustic Emission Technique, Test Interpretation and Numerical Simulation, where we'll explore the interaction between numerical strategies and experimental tests in the field of acoustical emissions techniques. We are honored to begin with the Professor Giuseppe Lacidonia, a faculty member of Politecnico di Torino, Italy, and now a distinguished professor of Wenzhou University of Technology, with extensive expertise in acoustic emission application. He will share insight into its use for challenging real problems. Following his presentation, we will hear from Professor Ferenc Kuhn, full professor in the University of Debrecen, Hungary, a leading expert in the fiber bundle model, a powerful numerical tool that could be used in the analysis of acoustical emission signal and damage progression in solid. Finally, my colleague Leandro Friedrich from the Federal University of Pampa, Brazil, and me, Ignacio Iturrios, from the Federal University of Rio Grande do Sul in Brazil, will present application of discrete numerical strategy simulating acoustic emission tests in structure. This webinar promises to be an excellent opportunity to understand how experimental techniques and numerical simulation can work together to unravel damage process in systems that fail in a spasmodic, sudden, or intermittent manner. Thank you very much. Please, Professor Giuseppe, if you like to begin.
Thank you, Professor Iturios, for your kind presentation. I can start here. This is the title of my presentation, that is Current Monitoring Techniques and Materials Fracture Characterization, the case of Garisenda Tower in Bologna, in Italy.
Giuseppe, we don't see your presentation.
I was saying that thank you very much, Professor Iturios, for your kind presentation. The title of this presentation is Current Monitoring Techniques and Materials Fracture Characterization, the case of Garisenda Tower in Bologna, in Italy. First of all, I want to greet the municipality of Bologna because give me the possibility to share you this problem related to the Garisenda Tower in Bologna. That is a very famous tower in Italy, together with the Asinelli Tower. They are the symbol of the Bologna and in a certain way of all Italy, related to their heritage culture. And I can start with a little introduction, saying that non-destructive testing methods, particularly the acoustic emission technique, are effective for monitoring the condition of historical masonry buildings like the Garisenda Tower in Bologna, which is significant given the numerous similar structures in Italy. This presentation summarizes my previous studies on masonry towers, present findings from the ongoing monitoring of the Garisenda Tower since May 31, 2019, and discuss the fracture mechanics features of the selenite rock from this site. Just a few words related to my previous monitoring of Ensign Tower in Italy. These are the towers of Alba, that is a city near Torino in Italy. And some years ago, we made with other my colleagues the monitoring of all the ancient tower in the Alba. This was published in some papers on important international journals. Then we made the monitoring of this tower. This tower is the Asinelli Tower in Bologna. This is the most tallest leaning tower in Italy because the tower is tall 97.5 meters and is leaning on the west side. On this monitoring, we publish some papers. Two of these are reported in this slide. The other tower, the shortest one, is the Garisenda Tower that is inclined towards the southeast direction and is in not so good condition now. Some words relating to the acoustic emission technique that all the people that is speaking now and probably is also hearing me in this presentation. But what are the acoustic emission? Acoustic emission are the spontaneous generation of elastic waves that starts from microcracks generated in a body. In this picture, I reported a symbolic material with a generating crack and the elastic wave that spread from this generating crack. And they are registered by two sensors applied on the external surface. These sensors are piezoelectric sensors and are able to detect signals in the field of ultrasonic sounds. On the right, I am reporting a schematic representation of an acoustic emission signals with its amplitude in volt and its duration in time that is of the range of microseconds, hundreds of microseconds. Then I can say that what the acoustic emission is emitted energy. Therefore, in a process of loading, in which you have, for example, the compression of a specimen, we have that the gray area is the dissipated energy. The red area is the emitted energy, and the sum of the dissipated plus emitted is the related energy. Therefore, as you can understand, the acoustic emission is not related to the fraction energy, that is the area under this curve, that is the gray area. It is a typical snapback instability where we have the maximum acoustic emission signals just when we have the catastrophic behavior. What was speaking just a few minutes ago, Professor Ignacio Iturrios. We can have a single snapback instability or multiple snapback instability. It depends from the test that you are doing. This fact is well explained in this paper that you can read if you want in the next days. I speak about acoustic emission monitoring in this presentation using a new device that we have in our laboratory of structural mechanics at Politecnico di Torino that is able to detect signals and send that signals, that data in a cloud wireless. Therefore, we can work sitting comfortably on the table on our office. It's not necessary to go on the site, take the data, and go again to the office to make the elaboration. What about the Garisenda Tower? The Garisenda Tower was completed in the early 12th century. It is now 48 meters tall and has a slipper line of 3.22 meters towards west-south direction, in opposite direction with the Asinelli Tower. It was originally 60 meters tall, but it was cut because it just inclined just after the construction. Therefore, now it is 48 meters tall, and is probably one of the most inclined tower in Italy, more than the Pisa Tower and etc. etc. We wrote some paper on this problem in the Journal of Masonry, International Journal of Mason Research and Innovation. In this picture I reported on the top the plan of the Garisenda Tower, and on the bottom 2 sections and 2 facades. You just see from the section and this facade how much inclined is the Garisenda Tower. What about the monitoring system? I'll just speak of some of the devices that are applied in the tower, and they are acoustic emission sensors, fiber optic sensors that was not from Politecnico di Torino for our laboratory, but was put by a firm that is named Smart Monitoring in Italia from the international group Osmos that is the principal airquark in France. Then there are also some thermometers for the measurement of the internal and external temperature of the tower. More recently was applied also a pendulum in the tower by the firm that is named Eretecno Company of Bergamo in Italy. All these data are synchronized with the UTC time reference. Therefore, it's possible to make correlation between each data that are detected by the various sensors. As regards the acoustic emission monitoring, the first devices was applied on the 31 May 2019 and is current ongoing for a total time of monitoring of about 6 years start to date. This is a representation, a picture that represents the acoustic emission device. We installed the first device that is named AE001 on the May 51, 2019. Then we applied another device that is named AE002 on 14 March 2023. Some technical data that are not so important in this case, but the acquisition of data is the sampling rate is fixed in 5 megasamples seconds and are at 16 bits. The sensitivity of sensor there are sensor with large band and sensor resonant. Therefore, it's possible to understand the variation of frequencies during the test and also the localization of the acoustic emission signals. In this picture, I reported the position of the 8 acoustic emission sensors of the apparatus A001. At the moment, at the beginning of the monitoring, there were also seismometer to understand if there are vibrations due to the earthquake or due to the environmental influence of traffic on the tower. This is the representation of the acoustic emission sensors in plan. Look here, we have here this sensor red that is from the apparatus number 1. And here there is an important sensor that is put on the external side of the tower that is very useful to make the localization of the signal inside the bulk of the material. These in red are the second group of the acoustic emission sensor applied. And by these two devices, we can understand the evolution of the damage in time of the tower. The tower leans towards east-southwest side. In this picture, I have synthetically represented all the hits detected by all the acoustic emission sensors that are 16, and up to this data, that is 16 February 2025, we registered 25,000 signals, especially 17,000 and half from the device number 1, and 7,000 and half from device number 2. This is also interesting because this slide, because here we can see the rate of acoustic emission signals per day from the device number 1 that is about regular, just up to the October 2023, when we have a sudden increase of the acoustic emission signals. But regarding the device number 2, we can look that the rate is not so regular. Therefore, here there is more problem that in this other side of the tower. This picture represents the application of the fiber optic sensors by the firm Osmos, and these fiber optic sensors are able to detect data with frequencies near to 100 Hz. Therefore, they are able also to understand the natural vibrations of the tower, more that detected the vertical displacement of the masonry itself. Here I have reported in plan the position of the 6 fiber optic sensors, and here there is a representation in axonometry of the 6 fiber optic sensors. What we found when we started monitoring, we found that during the winter season, we have naturally a contraction of the basement of the tower where the fiber optic sensors were applied, and in concomitance, we have had increasing in the acoustic emission hits. This graph represents the displacement of the basement of the tower detected by the fiber optic sensor, and we see that especially in this point we have an increasing in the vertical displacement that was not recovered. Some other displacement was recovered during time, but in this position not. It is just the east-west side of the tower. This is another interesting diagram in which we can see that each time there is cold in the tower, we have a sudden increase in the acoustic emission hits related to the apparatus number 1, and this continues from the starting of the monitoring up to January 2023. But as I just said you some minutes ago, in the 22 June 2023, we have a sudden increase in the acoustic emission events. It's look at this diagram red, and also a sudden increase in the acoustic emission of the device number 2. Therefore, in concomitance to an increasing of the contraction of the displacement, vertical displacement of the tower. Therefore, the area all around the towers was close to the person and also to the traffic. This diagram are also interesting because it represents the correlation between accumulated acoustic emission needs and the variation of temperature. You can see that when the temperature is low, around 10 degrees Celsius, 5 degrees, we have an increase in the acoustic emission. When the temperature is high, that is in summer season, we have not acoustic emission. And this is repeated for a lot of time. But starting from the signal number 6,000, we have not that is regular behavior. Therefore, acoustic emission, and that means microcracks increasing also during the summer season. This is for the device number 1 and also for the device number 2. This is the correlation that is similar between the train detected by the fiber optic sensor and the acoustic emission signals. When it's cold, we have contraction. Therefore, we have increasing in the damage that is represented by the acoustic emission. This is other interesting diagram because we made the localization of the acoustic emission signals. Naturally, was not possible to find signal in concomitance. Therefore, we made the localization considering 2 sensors per times. And relating to the apparatus number 1, this is the simple formula that we use. We found a lot of signals localized around the sensor number 2 that was in the middle of the bulk of the material, about 440. A total of 1,600 acoustic emission events was localized, considering that the total of signals was 15,700. This is the position where we found localized signals. For the other apparatus, the apparatus number 2, we made the same calculation, and we found on the left side, that is just near to the entrance of the tower, this number of signals that are few on the left, that is in the north direction, but more signals on the right, that is toward the south direction. Therefore, this is demonstrated that this is the most stressed side of the tower. As other words related to the pendulum was applied on 25 February 2021, and this is a section of the tower that represents the position of the pendulum. Naturally, it was not possible to start for the top and arrive into the basement because the tower is a lot of inclining. Therefore, we start from the 58 an height of 58 meters, and we arrive at an height of 10 meters. This is the direction of the pendulum. The weight of the pendulum is embedded in a glass contain oil, and the displacement, the horizontal displacement of the tower are calculated, detected by a telecoordinator that is a series of laser. What we found by the pendulum? By the pendulum, we found this data. In blue, there are the displacement of the top of the tower in the X direction, that is west-east. In red are the cyclic behavior of this displacement, while the straight line black is the residual displacement after each cyclic behavior. Therefore, this is the residual of the displacement during all the oscillation of the tower. The oscillation are elliptic because are related to the movement of the Earth and also to the heat of the sun around the tower itself. But some displacement are recovered, other not. the displacement that they are not recovered are the residual displacement, the vertical displacement of the tower. This is the residual displacement in the X direction. This is the residual displacement in the Y direction. And these are the final results of the displacement, considering all the oscillations that I previously showed you. Therefore, at the end of August 2024, we have a residual displacement of 1.89 millimeters. This is another interesting diagram that represents the position of the tower during each winter season. This is the cloud of all the position of the tower detected by the pendulum, and I can show you this series of diagrams. When we was in this season, on the winter of 2021, the tower was in the west direction. Therefore, we have not a lot of acoustic emission signals, as you can see here. When we was in the winter of 2022, the tower was in this position. Therefore, we have not a lot of acoustic emission signals. There were signals, but not a lot. Then the tower displays in this position, and when the area around the tower was closed, the tower was in this position. Therefore, leans more towards west-south direction. Now, the tower in August 2024 is in this position. Therefore, this is the reason why we have a sudden increase in the acoustic emission needs. Look here, the tower was more stressed on the sides that are in the east-south direction. As regards the fracture, the fracture energy of the material that composed the basement of the tower, that is more selenite. Selenite is gypsum. We made for the first time, probably related to this kind of material, the analysis of the fracture energy. We also made other tests in the basement of the tower, such as endoscopy, imaging, electric tomography to understand the pores that are in the selenite, and also other analysis like tower wall stratigraphy. These are three very rare specimens that we can drill from the tower. Now it's not possible to make other drilling because the tower is not in good condition, and we use these larger specimen to make the mode 1 fracture analysis test. This is an analysis by X-ray crystallography of that material, and we found that the material is selenite is practically gypsum because these are this chemical form. We also made some SAM scanning. This is a granite, this is selenite. You can see that the selenite is made by a lot of layers. Therefore, this is the reason why the selenite have a not large resistance if compared with the granite. Because that material was very, very brittle, we made the cut not with a mechanical device, but with a water laser. Therefore, by water laser was possible to make cut without destroying the specimen itself. And we obtained this kind of specimen that are very useful, that are utilized for calculate the fracture energy of rocks. These are little notch, impose that a fracture starts from this point and go almost vertically. This is a geometrical representation of the specimen. This is a apparatus to make the 3-point bending test, and we made the test using the RILEM Technical Committee recommendation. These are some photographs taken during the test in laboratory. You can see that the tests are conducted by crack mouths opening displacement. We also obtain the vertical displacement and the stress versus time behavior that is very useful to understand in which position in time are the acoustic emission signals. and the rate for the CMO test was fixed at 0.001 millimeter per second. These are the results obtained from the test number 2. It is a little bit strange because we have a very large curve. Therefore, this behavior was not so brittle. We load versus C-mode, load versus vertical displacement, load versus time. You can see here acoustic emission signals, the rate of the acoustic emission signal in red. In blue, there is the cumulate curve of the acoustic emission signal. Its or signals is the same. These are very beautiful curves obtained for the specimen number 4. This one, that is a very brittle behavior, and this is also a very beautiful curve obtained from the test number 5. Then we also made calculation to obtain the fracture energy compression. This is new because generally we done experimental tests to understand the fracture energy under mode 1. But in this case, is also useful to make this kind of test to put in a finite element model that was composed by Diana, the fracture energy under tension and under compression to generate a model that is able to calculate the smeared crack inside the basement of the tower. Then we made the tests considering specimen under compression, and the tests were conducted guiding the circumferential expansion of the specimen itself. We made six tests considering specimen of the same diameter but having a different slendernesses. Slenderness equal to 1 and slenderness equal to 2. This is a typical result of the test under compression conducted by the horizontal deformometer. Here we as represented the vertical displacement, here the circumferential displacement, and in red there is the variation of the volume. This is the summation of the deformation in the 3 directions, epsilon 1, epsilon 2, and epsilon 3, divided by V. You can see that when we have the maximum expansion in the volume, we are just near to the collapse of the specimen because we are near to the peak load, and also the horizontal displacement is increasing and increasing. This is the variation of Poisson ratio during the test, and this is the cumulative count of the acoustic emission signals. You can see that is the tower, no, excuse me, the selenite begin to emit acoustic emission near to a stress that is of 0.2 megapascal. This is a comparison between the behavior of this kind of material that is rock compared with concrete. If we have made tests on concrete, we have had a flex in this position, then the maximum, and then the collapse. In the rock specimen, there is not flex because there are not aggregates, because the presence of aggregates generates this flex in the variation of volume when we have the detachment between the mortar and the aggregate itself. These are tests that are very important to do in laboratory. And considering the fracture energy compression, we use this kind of model that is named overlapping crack model. In this model, we consider a first behavior of the material, considering the stress versus displacement here, that is linear. Then when we reach the peak stress, we use this other law. That means that we have a reduction in the stress, and when the stress reach the value equal to 0, we have the total compenetration of this kind of material, and this band of compenetration is similar to the band of process of fracture under under traction, okay? But it's very interesting because by this model, it's possible to find the traction and energy compression. And this is the results obtained by the stress versus the results obtained during the compression. These are the curves related to stress versus strain diagrams. But if we made the normalization of all these stress related to the maximum value, we found that the softening branch of the stress versus strain collapse all around to a band. That means that the fracture energy compression is an invariant parameter of the material. Then we use the test, the three-point bending test, and the test under compression to put this data in a finite element model of the tower to calculate the smeared crack. This is the model in few words and in few diagrams. The model have approximately 200,000 brick elements and 600,000 nodes. But what we found? We found that the model was highly nonlinear. Therefore, we increased the tilt of the tower, and we found the increasing of the smeared crack in the basement. And the results of this, when considering only that load, we found some cracks in this position that are very near the position of the acoustic emission device number 2. There are also some smeared crack in the ground, but it's not, we have not acoustic emission sensor here. But increasing and increasing the tilt, when we arrive at about 2.5 degree of the inclination, we have the generation of this smeared crack, and the tower must go to the collapse. I just go to the conclusion. The monitoring data of the Garisenda Tower from May 31, 2019 to February 16, 2025 reveals the following key findings. A correlation exists between an increase in acoustic emission signals and the formation of fiber optic sensors. Acoustic emission signals rise more rapidly during seasonal minima in fiber optic sensor deformations. Deformation measured by fiber optics indicate the tower is drafting versus southwest, a trend also observed through pendulum movements. This is important. The ongoing rise in the cumulative acoustic emission signals suggests that tower damage could arise from multiple factors: temperature variation and creep effects due to the structure's dead load. The characterization of cell and rock of Garisenda Tower using mode 1 fracture energy and the overlapping crack model in compression has been also presented. AE events are localized using the device number 1 and the device number 2 at a wave speed of 1,050 meters per second. And by the first device, we recorded 13 and 700 signals with 1,600 events, while with the second one, we captured 6,500 signals and 2,800 events. Therefore, there is more damage related to the device number 2 than to number 1. A nonlinear finding that the model with a smeared crack formulation was created to analyze foundation tilting. It indicates that a tilt of 2.5 degrees causes significant cracking in the tensile region, risking collapse, consistent with the acoustic emission localization findings from the AE002 device. I finish my presentation. Thank you very much for your attention. And the presentation is open for discussion, but probably I am late.
Giuseppe, you have a question in the question and observation of the Emiliano Sampetti. I read. it is possible to have details information about the PZT sensors? This is a question.
Yes, yes. If he wrote me an email, I can respond to you. I can respond to him because there are presently large band sensors with a sensitivity that is between 5 kilohertz and 2 gigahertz. And this is the sensitivity of the sensor. But I have all the data because that sensors are not sold by PAC device or Mistral's device, but realized by a firm in Italy, which name is Lunitech. If this scholar want, if he write me, I can send him all the data. Okay, thank you for the question.
Okay, thank you. Other questions or commentaries? Okay, I have more one question, Giuseppe. When you here Sina, you see in the
Yes,
webinar.
I see.
Yes.
Yes, I see. Can you read for me the
Yes.
question?
Hello. Okay. Hello, and thanks for the nice and useful presentation. For the acoustic emission data, did you use waveforms or only the future of acoustical emission data?
Yes, I understand the question. I have not time to explain anything, but that device is a parametric device. If you want to look the shape of the signal, you must put an oscilloscope there. But what we have from the acoustic emission data, we have the duration, the frequency, the peak voltage of the signal, the moment in which the signal reaches the sensor. Therefore, by that device, it's possible to make all the elaboration of the acoustic emission data, but the shape of the signal is not visible because if we take also the shape of the signal, we lost a lot of memory for the computer and was not useful. When we made tests in laboratory, we use national sheet. Therefore, we can also look by programs the shape of the signal and all the oscillation. Okay, but the device is useful to make long time monitoring in situ.
Okay. Thank you, Giuseppe. Thank you very much. Then we put my question. The last question. Hello, which kind of analysis has been done in this study? Abdul Bari Ramini is the question is of this person. In this
Yes,
student,
yes, naturally we can do a lot of kind of analysis. Professor Iturriot and also Leandro Friedrich are very expert on this. We can make B-value analysis, natural time analysis, and also some new analysis that you are done. I suggest you to read our papers. But in this case, I do not show all the analysis that we have done. I have also done a lot of analysis considering the value variation, and we found that when we are towards winter season, we have that the value tends to 1. When we are in a summer season, we have that B value tends to 1.5. That means that during the summer season, we have more distributed cracks in the basement, while during winter, we have coalescence of these cracks. Also, if the cracks are not visible to eyes, we know that during the winter season, we have coalescence of cracks. Thank you for
Okay,
the
thank you very much, Giuseppe. Other question, please send an email directly for Professor Lacidonia.
Thank
Okay,
you. Thank you.
thank you very much. Thank you very much. Please, Professor Ferenc, if you like to assume the presentation. Please, people, if you, the public, everybody, if you put the the question directly in the K and answer logo, is better for organize the presentation and the discussion. Okay, Ferenc? Perfect, Ferenc. Please begin.
Thank you very much. So I would like to thank for the opportunity to present our work here in this nice seminar. I'm going to speak about fiber bundle modeling of fracture phenomena. And here for us, the goal is to investigate the process of failure towards the final outcome, towards the catastrophic event at the end. And the main goal is to try to find some signatures of the imminent failure. And we do it in a simple fiber bundle model. The motivation comes from the fact that there is a large variety of natural catastrophes which are caused by the nucleation and propagation of cracks. Of course, there are many examples. The collapse of rock walls is one of those. Here, the steep wall of an open mine was collapsing. But of course, similar mechanisms play a role in the emergence of landslides and also in the break-off of hanging glaciers, where a huge ice mass is hanging in a steep mountain slope, and then when this let's say large amount of ice just breaks off, it has a huge destruction power in the valley below. Then of course at higher length scales we have to mention the earthquakes, and then in the previous presentation we have seen that sometimes also engineering constructions may collapse. So here today it's a great motivation to develop methods to try to forecast the imminent catastrophic event at the end. And of course the basic concept of forecasting is that the catastrophic failure at the end of the process doesn't occur abruptly, but it has signatures. Especially the dynamics of process accelerates in many cases as the system approaches failure. And this acceleration can be described by such critical scaling law. Here, this omega denotes a kind of general quantity which characterizes the system. And then the acceleration means that the time derivative of this quantity has this overlaw dependence on time. But here, TF is the failure time, the time of the catastrophe. So you see that as we approach failure, this formula, this expression predicts a kind of overlaw divergence of the rate of change of omega. So we have an expression which contains the failure time. So that means that just using fitting or kind of approximation techniques, we can try to forecast the imminent failure of the system. Of course, the quantity omega depends on the system that we study and depends on the measurements we can carry out. For example, in these creep rupture measurements, the strain rate was monitored. So actually the strain rate could finally nicely, the strain rate exhibited this nice power law behavior. So you see the red line which fitted the data with quite a good quality. Then in the same laboratory experiment, acoustic emissions were also monitored, and the rate of acoustic events had a similar power law acceleration towards failure. Then one more example, before volcanic eruptions, earthquake activity can be measured, and then here the daily rate of earthquakes have a similar functional behavior. Again, quite a good fit could be obtained. Then, of course, forecasting means that before the catastrophic event, we, let's say we are somewhere here, and then we try to use this expression, this formula for fitting, and then by fitting, we approximate we have a good approximation of the failure time. Then, of course, the precision of this estimate depends on where we try to do, where we are in the dynamics and where we try to apply this fitting procedure. Here you can see the horizontal line is the actual failure time that we get in the experiment. We know it, of course, when we finish the measurement. And then these dots are the estimates of the failure time, which were obtained at different time fractions of the evolution. And this, of course, obvious that as we approach failure, the estimates are becoming better. then it's always true. So the precision towards failure is increasing. If we have more data, or if we are closer to the catastrophic event, we can have a better estimate. Then recently, some interesting experiments were carried out about the role of disorder in the forecastability of catastrophic failure. Especially in this one, some synthetic materials were used, and then acoustic emission experiments were carried out. And the authors tried to use this failure forecast method to estimate the failure time. And then it turned out that actually forecastability depends strongly on the degree of disorder of the material. At higher disorder, one can get a larger amount of precursors, and then of course that can improve the precision of forecast. So actually this was the motivation for our work. We wanted to use a fiber bundle modeling techniques to better understand the role of disorder in failure of heterogeneous materials, especially the role of disorder in determining the amount of precursors before failure. And then on the other hand, we wanted to propose another strategy for forecasting. Our idea is that instead of forecasting the failure time, you could try to find a clear signature of the onset of acceleration towards failure, and that would mean kind of safe. This is the point where kind of safety measures could be made on time before the structure collapses. So then let me just describe the fiber bundle model first. For us, this is a very simple approach, maybe the simplest one to the fracture of heterogeneous materials. The main advantage of the fiber bundle model for us is that it gives us the opportunity to have a very simple, very efficient representation of the degree of disorder of the materials can have. So we take a piece of material, and then this is discretized in terms of a set of parallel fibers, where these fibers are arranged on a regular lattice. It's always a question whether the spatial arrangement is important or not. Then the fibers are not glued together, which means that the bundle can support load only parallel to the fiber's direction. Then under slowly increasing external load, about the mechanical behavior of fibers, we assume that they have this linear response up to a threshold load where they irreversibly fail. So then each fiber is characterized by two parameters, the Young modulus and the failure threshold, the strength of the fiber. And then, of course, in the simplest case, we assume that the Young modulus is constant over the fibers. But to capture disorder of the material, we assume that this strength of the fibers, the failure threshold, is random. And this is described by a probability distribution. Actually, in the simplest setup of the fiber bundle model, this point is the only one where we can really capture some material dependence on material properties. Then if we assume to carry out stress controlled loading, then after some time we reach the smallest failure threshold, and then the fiber breaks. Then the load of the broken fiber has to be overtaken by the remaining intact ones. So the load has to be shared by the remaining intact fibers. For load sharing, load redistribution, typically two extreme cases are relatively easy to study. One extreme is the so-called equal load sharing, which means that when a fiber fails, the load dropped by the fiber is equally shared by all the remaining intact ones. In this case, all the fibers share the same load. That means there are no stress fluctuations in the system. So practically, this is the mean field limit of the fiber bundle model. The other limiting case, and also very relevant for practical purposes, is the localized load sharing, which means that the load of the broken fiber is equally shared only by the intact nearest neighbors in the lattice. And this implies immediately large stress concentration around cracks. So we studied both cases in our model. Then for us in the modeling, it was important to have an opportunity to control the degree of disorder. That's why we decided for this functional form for the disorder distribution, for the threshold distribution. So it's a Power law where the threshold values can have values between two bounds, two limits, where the lower bound of the interval is fixed. It's just one. That means immediately that we have two parameters to control, and especially to control the degree of disorder. One is the upper bound of the strength values, which can change from the lower bound up to infinity. Yeah, so from zero widths to infinite widths of the distribution, and then the exponent here. So we have these two parameters, upper cutoff of the strength values and the exponent to control the amount of disorder. The nice feature of this model is that in the limit of equal load sharing, so when we assume that after each failure event, fibers share equally the load, we can solve it analytically, and we can even construct the phase diagram of the model on the plane of disorder parameters. So here you see the exponent on the horizontal axis, exponent of the distribution, and then on the vertical axis, you see the upper cutoff. The key point here is that at any value of the exponent, if the upper cutoff is too small, meaning that the distribution, disorder distribution is too narrow, we obtain brittle behavior, perfectly brittle behavior, which means abrupt failure. Already at the breaking of the first fiber, the entire bundle will collapse. Then if the distribution is sufficiently broad, when the value of the upper cutoff is sufficiently high, then we obtain stable cracking, so fibers can break in sequences, and then the system approaches failure through breaking sequences of fibers. This is what we call quasi-brittle behavior, and then we can determine the phase boundary between the two regimes analytically. And then it's visible that here disorder has a substantial role in the failure process. This was crucial for us. Then when we subject this bundle to a slowly increasing external load, the key point is that the failure process, the failure evolves through avalanches of fiber breakings. This means the following: we slowly increase the external load to break just a single fiber, and then the load dropped by the fiber is redistributed in the bundle. Then this implies immediately load increment on the intact fibers. So there may be fibers which exceed their breaking threshold, then we may obtain triggered breaking. But again, this triggered breaking will be followed by load redistribution and so on. This load redistribution may be followed again by triggered breaking. So starting from a single fiber breaking, we can generate a cascade on avalanche of fiber breakings. Actually, in the fiber bundle model, these avalanches, breaking avalanches, correspond to the acoustic emissions, what Professor Lacidonia presented in the previous talk. Yeah. Then for the case of equal load sharing and for moderate amount of disorder, one can prove analytically that the size of bursts, that is the number of fibers failing in avalanches, is power law distributed, and the exponent is also kind of universal, 5/2, at least for these type of distributions. And then here I plotted the size of avalanches as a function of load where they occurred, and you see that there is a kind of acceleration of the dynamics. The fluctuations are increased towards failure, and the average size of the burst is also increasing. So just looking at this image, it's visible that we have a chance by analyzing the structure of this evolving sequence of events to forecast the upcoming failure, global failure. So in our model, we have the possibility to tune the amount of disorder. That's why it's good to look at the behavior of the system in the limit of very high disorder when the upper cutoff is infinite. This is what we obtain. So we have a stationary sequence of events. So this is just the size of avalanches as a function of the order number. They are just counted. This is kind of natural time. It's called, and you see the moving average is also quite a constant. So it means that in the limit of very high disorder, the failure process of this bundle is kind of unpredictable because we have a stationary evolution. It's still true that the statistics is scale-free, so the size distribution of avalanches is power law. The only role, the exponent is 3/2, and the only role the exponent of the distribution, this exponent nu has, is that it controls the cutoff of the distribution. Then if we check the behavior of the system, when the amount of disorder is a little bit smaller, so I call it moderate disorder at finite upper cutoffs, this is what happens. Again, we observe a kind of stationary behavior at the beginning of the evolution, but then close to failure, we see a kind of acceleration of the dynamics. We see that the average avalanche size is increasing, and then, of course, the load increments between the consecutive events is decreasing. So this is what we want to characterize somehow. We would like to obtain a kind of signature of the onset of acceleration towards failure by analyzing the structure of this sequence of events, sequence of avalanche sizes. So our suggestion is to focus on special events of the time evolution. These are the so-called record side events of the time series. For us, record is like records in sports. Record is an event here, an avalanche, which has a size greater than any previous event. And if you assume that the first event is a record, the very first one, then using this condition, you can really identify the consecutive records one by one, which form a kind of monotonically increasing subsequence of the evolution. So this is the first record. You see the red line here, then the second one, third one, fourth one, and so on. The distance is increasing. So these new records are always greater than the previous one. And then again, as we approach failure, you can see that even record breaking is getting faster and faster, and finally we get failure. The advantage of looking at records is that these are always the largest events. So kind of easy to handle them, easy to identify them, because we are not searching for something inside this noisy background, but we have to check the most dominating events in the time evolution. Then to characterize these record size events, we can introduce a couple of quantities. Records are identified by order number, by the rank. Then, of course, we have their size. And they occur at a certain event number in the sequence. This is the event index. And then we can look at the increment between consecutive record size events. But finally, one important quantity is the waiting time between two consecutive records. This is the number of events the system has to generate to overcome the last record. This is the kind of lifetime of the record size events. So these are the main quantities we looked at to really understand how we can profit from the record statistics of avalanches when we study fracture phenomena. As a reference, it's good to have a look at the case of pure randomness when we have a sequence of independent, identically distributed random variables, and there is definitely no correlation in the sequence what we analyze. So here I just used an exponentially distributed random numbers, and I plotted them as a function of the order number, and then you can easily see that we can, of course, identify here records, and I here colored the subsequences of the sequence of exponentially distributed random numbers between the records. Then it turns out that the statistics of records for the case of IIDs has some universal features. First of all, the number of records which occurred up to a certain even number grows logarithmically with the event number. This is very interesting. And this doesn't depend on the distribution that we use for the random numbers, for the independent random variables. Also, if we fix the value of the event number and just look at the distribution of the number of records we get, it has always a Gaussian distribution. Then the lifetime of records is crucial. This is the number of events the system has to generate to break the previous record. And you see it's monotonically increasing. It's a numerical calculation, so we have fluctuations here. Of course, this lifetime of records has to increase because record size is growing. That's why it's becoming more and more difficult to break the last record. And then finally, the distribution of record lifetime has a p-value function of form, and even the value of the exponent is kind of universal, doesn't depend on the random numbers, distribution of random numbers. So then the question is, when we analyze record size events and the statistics of records, the question is whether record breaking is only governed by statistics, like here in the final of 100 meter sprint, or there is something in this record size event. And our answer will be positive about this special features of record size events. So let's see what happens in our model when we carefully control the degree of disorder. So this figure shows the evolution of the average number of records which occur up to a certain event number in such case where we have acceleration at the end. So you can see that we have logarithmic increase initially, for small even numbers, but then towards failure, a kind of acceleration occurs. But then this parameter lambda characterizes the distance from the phase boundary that we had in one of the initial slides, which characterizes the phase boundary is the boundary which separates the brittle failure from quasi-brittle failure. Of course, we observed avalanches only in quasi-brittle failure, but when we are close to the case of perfect brittleness, when we are close to the phase boundary, then we have only a small amount of acceleration. Then we are very far from the phase boundary, close to, let's say, infinite upper cutoffs. Again, we have a long logarithmic regime and just a very short acceleration period at the end. And in the intermediate regime, we have a broad acceleration regime before failure. So this is the regime where we have a chance to somehow forecast the imminent failure event. The functional form of these curves can be characterized, the acceleration especially can be characterized by this exponential form. So we observed that the number of records strongly depend on the amount of disorder in our system. Similarly, very interesting is the lifetime of records, how they evolve in such a fracturing system. This is a very important outcome. Again, you see the average lifetime of records as a function of record rank for different amounts of disorder. You see at low disorder, close to the case of perfect brittleness, and at very high disorder, when we have practically ductile failure, we have a monotonically increasing lifetime. Monotonically increasing lifetime, which means everything is controlled by disorder. But then at intermediate disorder, what we see is that initially the lifetime of records increase, which means that the initial regime is controlled by disorder in the fracturing, but at a certain point in the dynamics, we see that the lifetime starts to decrease, record lifetime starts to decrease. That means record breaking accelerates, and we approach failure through the acceleration of the breaking of records, consecutive records. And we can identify the record rank, the rank of that record which has the highest lifetime, and of course that separates the two regimes. So the final outcome of this argument was that this analysis was that the beginning of the failure process is controlled by disorder, and this shows up in the record breaking process in such a way that the record breaking slows down because it becomes harder and harder to break the previous record. But when close to failure, when stress enhancement after avalanches start to overcome the control in the failure process, we observe the acceleration of record breaking. And then the two regimes are separated by this critical record rank, by the rank of the record which has the largest lifetime, or actually the record after the longest living record. So it means that looking at the record breaking process during the failure of these heterogeneous materials, analyzing the record statistics of acoustic emissions, we may be able to identify the onset of acceleration just by identifying the longest lived record. Of course, it's a question how significant the maximum of the lifetime is. That's why we calculated the difference of the rank number of the record which has the highest lifetime and the last record in the experiment, in the measurement. And then we also determine the lifetime of the longest living record and the lifetime of the last record in the system. Again, here you see these quantities plotted as a function of the amount of disorder, about the distance from the phase boundary in the disorder plane for different values of the exponent of the disorder distribution. It's clear that at low amount of disorder and at very high amount of disorder, the acceleration is not significant, or it's not even present. But there is a well-defined disorder window of disorder where we can have the chance to have good predictions, or we can make an early prediction, early identification of the signature of the acceleration towards failure. Then we studied the entire disorder plane. So here you see this data K quantity, the difference of the record rank of the rank of the last record and the record which has the highest lifetime on the plane of mu and lambda. And you can see that when we are close to perfect brittleness, close to the phase boundary, we have only a few events before failure, and everything is controlled by the disorder, this low amount of disorder that the system has. So we have no chance for forecasting, there is no acceleration. The same happens in the limit of very high disorder, where we have kind of ductile failure in this simple model. We have again a stationary evolution of avalanches with a steady moving average. Again, no chance to identify acceleration. But in between, there is a kind of optimal amount of disorder, a range of disorder, where we have a good chance to identify early signatures of the imminent failure. At least we can identify a clear signature of the onset of acceleration towards failure. Then, of course, it's a question how general this mechanism is. We studied the role of the range of load sharing in the statistics of records in fracture processes. So here, this is the same fiber bundle model, but no fibers are really assigned to a sides of a square lattice, and we used localized load sharing. Here, the black areas are cracks, and you can see that the along the perimeter of cracks, we have large stress concentration. Of course, this stress heterogeneity, together with the disorder of fiber strength, plays a significant role in the in creation of the avalanche sequence. This figure compares the case of equal load sharing, what you have seen before, and the case of localized load sharing. So this the high values of delta K here above the disorder plane are the data what you have seen in the previous slide, and the localized load sharing place are this dark green area. You can see that in the case of localized load sharing, when we have strong stress concentration around cracks, then the acceleration is less significant because failure becomes much more abrupt, but still there is an optimal amount of disorder, there is a range of disorder where we have a good chance to forecast failure. And the last example is, let's say, compressive failure of geomaterials, where we used a discrete element model to simulate the compression of sandstone samples that had been performed in the laboratory. And then we obtained synthetic time series of acoustic emissions, so synthetic time series of avalanches of the breaking of contacts of particles. And then we observed similar behavior. So we constructed the synthetic series of avalanche sizes. And then when we analyzed the statistics of records, we observed the same acceleration of record breaking towards failure by looking at the average lifetime of records. When we reshuffled the data, when we, let's say, randomly rearranged the avalanches in the sequence, then this is the blue, these are the blue triangles, the effect disappears. So actually it shows that the reason of the acceleration of record breaking is really the increasing role of stress enhancement following the avalanches of breaking contacts here and breaking fibers in the fiber bundle model. But here again, we can identify a clear record rank, which is much smaller from the compared to the largest rank of the largest record. So we have really a large number of records even after the one with the longest lifetime. So just to conclude, our suggestion is to use record statistics to try to forecast to identify a clear signature of the onset of acceleration towards failure. We show that record statistics is very sensitive to the degree of disorder, and especially it can be used to characterize the competition of disorder and the role of and the stress enhancement in the failure process. We can use the record with the longest lifetime to identify the point of the onset of acceleration towards failure. So we think that this should not be used as an alternative method compared to the other ones, but it could complement existing methods when we analyze the statistics of records. I think I'm almost on time, so thank you very much for the attention.
Thank you very much for very interesting presentation, Professor Ferenc. I have a question, but first the other people. There are some questions. Well, my question is, I see the tendency that you show in the slide, but you compare this result with other kind of precursor, for example, for the evolution of B value or for the natural time parameters that is possible we use as precursor, because you understand me?
Yeah, sure. But in those methods, you try to forecast the failure time, I guess. But here we are not forecasting the failure time. We just want to identify the point where acceleration starts.
Okay.
And then just looking at the statistics of records, we also can quantify how broad the acceleration period can be, depending on the degree of disorder.
Yeah, okay. And another question. There are a question of Sina Sarabi. Sorry, because your name is very complicated for me. Many thanks for your amazing presentation. Shoot a short question. In the last example, did you use FEM with a program or use a random particular modeling?
Actually, I was using a discrete element model, so not finite element, but discrete element. That means that here in the model, we had a packing of particles. These were spherical particles with a log normal size distribution, and they were coupled by elastic beam elements. And then we compressed the samples, and then we identified avalanches of the breaking of these beam elements, which connect the particles, by looking at the temporal correlation of consecutive local breakings. So we could construct this series of avalanches by analyzing the cascades of breaking of the contacts of the particles. But this was purely discrete element and not finite element.
Okay, and I don't know if you okay. I have other question. I have one question. In your model, you consider or not the inertial force, for example, because when some bonds break in a real structure, produce some inertial perturbation. But in your model, you consider this or not? It's a quasi-static.
In this model, in the discrete element, it can be considered, of course, that is included. But in the fiber bundle model, that's too simple for this. Yeah.
Okay.
That focuses only on the statistics and the role of statistics.
Yeah. Okay. Thank you. Well, many questions?
I have a question.
Okay.
Thank you, Professor Kuhn, for your very interesting presentation. Did you try to apply your theory to forecasting earthquakes, for example?
I would be happy to get some data and to use it for this, of course. Sure.
Yeah.
And actually, we are trying to get some acoustic emission data from experimental groups to try to apply this approach.
Okay. And you found something, for example?
So if you not yet, but if you have some data, I would be very happy to analyze. If you have this, I have seen in some of your plots that you have some acceleration, a tendency to accelerate in the acoustic emission. So we could analyze it. I would be happy to do that.
One interesting, the first formulas that you show with the exponent minus p is exactly the contrary of the Omori law, because in the Omori law you have high events at the beginning, then you have a decrease in amplitude. With that law, because the exponent is minus p, you have the exact contrary. You start from low data and you arrive to high data. Therefore, if you think on this fact, no, we can add another law to the study of earthquakes, because after the main event you have the Omori law. Before the main event, you can have that law, and is interesting. I suggest you that you, Professor Ignacio Iturrioz, Leandro, can write a paper on this fact.
I see. Then we should keep in touch after the seminar. Yes, sure.
Because I was tutor of some thesis on this argument, and I found the same law that you show now. And I have a lot of data. We can have a speech together. And
okay.
It's
thank you very much. It's very interesting.
Yes. Professor Alex Hansen have a question, and I read. Thank you for your beautiful talk. Are there any trace of the 3 extreme value distribution, Frechet, Weibull, Gumbel in the theory? The question is in the KA.
I see.
Okay.
This is of course very interesting. We haven't tested yet, but you are right that in the statistics of records, somehow these three distributions should show up also. But I don't have a good answer to this question. But it's of course it's very interesting, definitely. We haven't checked this. But thank you for the question.
Okay. Any questions? Okay. Thank you very much, Professor Ferenc.
Thank you very much.
Okay.
Thank you very much.
Now I introduce me. Okay, thank you very much, everybody. My name is Ignacio Iturrioz, and this is the title of my presentation, Application of Discrete Element Strategy to Aid the Interpretation of Acoustical Emission Data in the Damage Process of Structure. I organize my presentation in this way. I speak about three keywords: phase transition phenomenon, acoustical emission technique, and simulation using discrete element method. About the phase transition phenomenon, it's important topics on the physics statistic. The phenomenon happens when the matter change of state, solid, liquid, or solid to liquid, liquid to gas, but also in quantum mechanics, in change of magnetization properties in function of the temperature and in the rupture of quasi-brittle material, such as rocks, concrete, ceramic, and composite. In this last example, is linked with more general problems called crackling that appear clearly in the famous Gutenberg-Richter law. These changes are due to collective behavior. No changes are produced inside the atoms or molecules when the phase transition happens. In phase transition problems, universality and autosimilarity are two characteristics that are always present. In the universality, the function and coefficient that govern the behavior near the critical regime, where the transition phase happens, are the same for groups or material classes. This property is important because few laws could be explained a lot of apparently very different situations. Well, if we like to represent, for example, a region, a spatial region, in this case is 2D region, with local situation, we have break or mark in black and unbreak mark in white, or region with paramagnetic situation or ferromagnetic situation, or some part is liquid and other part is gas, it's possible we apply some method to pass the information in quartz mesh, and then we rescale. If we apply this procedure in sequence, in successive form, it's possible we see this situation. This situation. When we stay in the critical or close to the critical regime, it's possible we see that in this dominion that I present, the pattern not change. Here the pattern not change. But if we stay in far to the region in which the phase transition happened, it's possible we see that the pattern changed. Here we became to all is white, and in the bottom we came to all the points are black. Why? Well, in the middle, we have the autosimilarity behavior, and it's possible we represent the behavior of this the what happened in the critical regime using some function that is a potential function. In the other cases, it's not possible because when I change the scale, the results change, and for this reason, the results are a function of the scale. This is the first keyword. The second is about the acoustical emission technique. Well, the Professor Lacidonia speak about the definition of acoustical emission technique, and I don't repeat. But with the information we obtain with the acoustical emission technique, it's possible we compute some global parameter. Well, the most, I think, the most famous is the B value proposed by Gutenberg Richard, but used by different researchers. In the idea of the B value is we obtain the declivity in the B-log plot, in which present the statistical distribution of the amplitude of the event in some window. Here we present, for example, two very different situations. This is a little composite beam, and in this case we analyze a result of the work with Professor Giuseppe, in which some region of Italy is analyzed in terms of the head weight. It's possible we see in the two situations that when the B value fall, the B value here, I present only the B value obtained in different windows. And it's possible we see that when V value fall, it's possible we see that the acoustical emission activity increase. And in the case of the head weight, it's possible we see that a big head weight appear when the B value analyzed is decreased. Okay. Then I speak about the third keyword is about the discrete element method. There are many of these methods. Well, the fiber bundle model is one of these, and the Professor Feng mentioned the particular method proposed originally by Kundal. But here our group work with two strategies, but this is very similar. One is the peridynamic approach. In the peridynamic approach, and the other is is a version of the lattice discrete element method. In the peridynamic approach, we have points, material point with mass, and in a region that I will define I define with a radius of horizon. This is delta. We call horizon. We connect all the points that is inside this region for the X point. If I change the point, I use the same radius, and we connect other points with the bonds. Okay. In the case of the discrete element method, we use a fixed range for the bars, and but there are a similarity of the two strategies. When in the case of the peridynamic, we use very simple, similar to the fiber bundle model, a simple elastic law with a brute cut in some random value of the strain. This value has some statistical distribution. In the case of the lattice discrete element model, we have a bilinear law, and also we introduce here the random behavior using different value of the area below the curve. It's possible we see that the value of the strain, the critical strain, is 0 in this case, and in the epsilon p is the expressions are similar, or in both cases we have square root, and we have the toughness G0 GZ, and we have the elastic module A, and here we have the horizon, and here we have the equivalent D. Both distance are a characteristic distance of the material. Is both parameters is not numerical parameter, are the material parameter. Okay, well, then in this way, in both methods, we obtain some motion equation, and it's possible. The motion equation have the mass in the node, the some damping, and the internal and external force are also computed. It's possible we apply some explicit. I like to use. Okay. I don't know. Okay. It's possible also I use some explicit scheme of integration and solve the problem. Okay, it's possible using this method because we integrate in the time. I obtained a simulation of the acoustical emission test. It's possible directly put a virtual sensor in the material points, and I obtain the acceleration in this point. This is one. One direct method. Other method is if I in all the step I compute the kinetic energy. And if I derivate the kinetic energy, it's possible I obtain information that is very similar to the acoustical emission test. It's not the same because we don't have a delay, but is the shape of the waves are similar. Okay. Well, about briefly about, because I have only 10 minutes, about the application. We have here, we present here some application. Is a prism of basalt, and with an inclined fissure. And when I program the test, I use, we don't have a very good programmation, and we use some we introduce some flexibility in the support. And for this reason, the way that this body break was complicated. But also we simulate this situation using them, and when we simulation using them, we put very good supports, the rigid support, and we have this response. In the experimental response, it was totally, it's not totally, but very different. But, well, this is wrong. Well, it's interesting because in this case, we have a benchmark to test a different situation in which appear local instabilities, and we see if the B value and the others parameters would be indicate if the local instability appear. For example, in the p-value is possible. We see here that when more, this is the acoustical emission information, and it's possible we see that when some local increment in the acoustical emission activity appear, we have some fall down in the p-value coefficient. This p-value is obtained in different windows during all the test. This is the other parameters that is obtained by the Devsky, Pradhan, and Hansen, but I lamentably I don't have time to explain this now. Okay, other application is, in this case, we don't have experimental test to compare, but is applied with a pure shear solicitation, and it's possible we see that when the p-value decrease, the failure is imminent. The failure happened in G, and it's possible we see here that here appear a clearly change in the regime. This p-value is with this when have this behavior in the p-value is indicative that the critical behavior is near to happen. Also, interesting information is here we have a region that we accumulate some damage. This region have this happen near in the eminent close, and it's possible we see that this dimension is the equivalent D, is proportional to the equivalent D dimension. When we have a fissure with the equivalent D dimension, it's possible that this fissure propagate when apply some critical level of stress. The last example that I'm very curious to know the opinion of the Professor Ferenc, all of the other person, obviously, is I try to simulate in a very not conventional way the fiber bundle model. I consider with them rigid support, not totally rigid. It's a support that is see as rigid with the bones, and I put here an acoustical emission sensor, and I obtain this curve. This is the results in terms of the load. This is the accumulate acoustical emission events, and this is the amplitude of the acoustical emission. And this is the information in terms of the energies. These two, we compute in this case different precursors. The Professor Leandro then speak about in the continuous the presentation speak about these precursors. And for example, here we have the P2 is the p-value, and it's possible we see that the p-value decrease when we stay near the maximum value of the law. In this case, for this reason, my question, Professor Ferenc, in this case, I consider the acoustical emission. I think I don't know if this make sense. For this reason, I like know your opinion. Here we present the results in terms of the normalized time during all the process, and this is the spatial time. This is the model is 2D. And in black, we consider in which way all the bars are broken. In light blue, we don't have broken bars, and in red we have the break bar. Okay, this about the conclusion. Well, we speak about the three keywords. The global parameters computed from the signal captured in the acoustical emission technique could be used as a precursor to the proximity of local or global collapse. This fact could be understood in the phase transition framework, and the simulation using the discrete element methods of the acoustical emission technique in a structure could be given complementary information aid the real acoustical emission interpretation. Now I close my presentation, and please, Professor Leandro, put your presentation.
Okay, good morning, good afternoon, everyone. I'm Professor Leandro Ferreira Friedrich from Federal University of Pampa, and I will continue the presentation of Professor Inácio, named the application of the discrete element strategies to aid the interpretation of acoustic emission data in the damage process of structures. And I will focus on present some case studies by employing discrete element strategies. In the last years, we have been working in the development and application of precursors, index, and parameters in order to know how and when the structure will fail. In short, failure precursors are signs or indicators that may precede the occurrence of a failure in a system material or structures. There are several ways to collect this kind of data and to apply these monitoring parameters by using, for example, experimental tests, numerical simulations, and the seismic data. In this presentation, I will focus on the numerical simulation and the acoustic emission data from numerical simulations. Here are some precursor parameters that you have been employing in order to identify the critical condition in the structure. The first one is the p-value that the Professor Inácio already explained, the natural time analysis, and the last one is a novel approach based on the method of critical fluctuations that we call MCFB approach. Due to the time, I will not present in detail each of these parameters, but you can find more information about them here in these three references. As Professor Inácio said, the p-value, it's a classical parameter in order to identify criticality, and it's following the Gutenberg-Richter relationship that related the accumulated number of acoustic emission signals and their amplitudes. Here we have the procedure in order to compute the p-value. Our experimental tests and numerical results by using this data, we observe a progressive decrease in the p-value as the structure approaches failure. Therefore, this is the signature when we employ the p-value in order to know if the structure will fail. The natural time analysis, it's a recent tool developed by Varotsos to identify when the complex system enters in a critical stage. And basically, in natural times, the conventional time between events is ignored. Here in this figure, you have a conversion of the conventional time to natural time. But it's preserved the energy of the event that in terms of acoustic emission could be the amplitude of the acoustic emission signal or the acoustic emission energy and another feature that characterize the acoustic emission event. And of course, the natural time is here. That is a ratio between the key event divided by the total number of the events in the time series. Details about the natural time analysis can be found in the book of Varotsis, Natural Time Analysis, The New View of Time. In natural time analysis, 4 parameters should be computed: the natural time invariance, the entropy on the time reversal, and also the average distance. These 4 parameters have a critical value, and therefore are used to identify when a critical situation is going to happen in the system. To know this critical condition, three situations have to occur at the same time. The average distance d should be smaller than 0.01. The variance when descending from above approaches 0.07, and both entropies should be less than the entropy of uniform noise, that is 0.0966. Therefore, when these 3 critical values are reached at the same time, we can see, based on the natural time analysis, that the structure is approaching the collapse. It's important to say that in many cases, we are able to identify also small instabilities during the loading, for example, but also a critical condition, that is the failure of the structure. The last parameter is the MCFB approach that was proposed by Professor Inácio, and also Professor Giuseppe, in a paper that we are looking for a way to measure the loss of linearity of the Gutenberg-Richter relationship. And therefore, basically, we now modeled the accumulated number of acoustic emission signals by using an equation formed by 2 exponents. One is the P2, that is a power law decay exponent, and we are also the value of P3, that is exponential decay. By monitoring these 2 parameters, we are able to take into account the deviations from the data linearity that we have been observed in both numerical and experimental data. In this way, therefore, we can evaluate the loss of linearity in the frequency magnitude relationship of the events. And also, we created this function based on the method of the critical fluctuations, but always inspired in the crossover phenomenon observed in the fiber bundle model. In a previous work, we identified that a signature of a critical condition of the MCFB approach is defined as the presence of a perfect power law, and then simultaneously the decrease of P2 and the monotonic increase of P3. Therefore, it means that the perfect power law, the value of P3 is equal to 0, and therefore we have a power law governing the behavior of the accumulated number of acoustic emission. However, when approaching the failure, the value of P3 started to increase, and therefore changing the shape of the accumulated number of acoustic emission signal. As I said, similar to the crossover phenomenon observed in the fiber bundle model. So let's see some case studies. The first is a comparison between experimental and the numerical simulations using the lattice discrete element method that Professor Inácio presented previously. Here we analyze a concrete specimen under compression. The test was performed at Politecnico de Torino. And in this case, was a concrete cube, and was employing 8 sensors, 2 per phase, and the test duration was 51 minutes. More information related to the test can be found in this reference. By following the same setup of the experimental test, the lattice discrete element model was employing, and here you have the numerical parameters that is used in this simulation. As Professor Inácio said, in the LDIN, it's possible to capture the acoustic emission signals by employing a virtual sensor, like a real acoustic emission sensor. So the sensor is put in the surface of the sample, and the variation of the acceleration is recorded during the simulation. So first of all, let us compare the results against the load against the normalized time. Here, comparing the experimental and numerical results. And it's possible to see that the numerical results have a good agreement between the experimental one. And in the figure, in the second figure, we can see the balanced energy during the simulation. It's possible to see that the kinetic energy has a very low value, indicating that the simulation occurs at a quasi-static manner. Regarding the natural time analysis, here we have the comparison between experimental and numerical results. It's possible to see that in the experimental case, the critical condition of natural time, that is the value of the variance and both entropy and the average distance reach their critical values. Therefore, here, according to the natural time approach, the structure is closer to the collapse. It's important to see that the value, the normalized time equal to 1, is the time of the failure of the cube, the concrete cube. Therefore, it's possible to see that the natural time is able to identify criticality with some instance before fracture. By using the acoustic emission data recorded by the lattice discrete element model, it's possible to see a very good agreement between the areas indicating the criticality. And again, this area obtained from the numerical results is very close to the time of the collapse of the structure. In the second precursor parameter, we analyze the MCFB approach, but here just using the experimental data. And it's possible to see here we have the values of P2 and P3 during the normalized time again. And it's possible to see that perfect power law, you have the increase of the value of P3, indicating therefore the critical signature of this approach. And again, it's possible to see that is a region very close to the time of the failure of the structure. In this second case study, we employed the peridynamic theory in order to simulate a 4-point bending test of a concrete beam. Here are the dimensions of the beam. And by following the same experimental setup, we perform also the simulation. Here is the 3D peridynamic model. And in this case, we also record the acoustic emission events by monitoring the acceleration of some point localized in the surface of the beam. With this data, therefore, we separated the acoustic emission signals and applied the precursor parameters. It's possible, it's important to mention that in order to simulate quasi-brittle materials, we have to change a bit the original formulation that was presented by Professor Inácio. Basically, we have to add a bilinear law in order to govern the behavior between two material points in the peridynamics, to take into account the post-peak softening behavior that is typical observed in this kind of material. And at the same time, we have to take into account the heterogeneity of this material, and therefore we employ a 3D random field of the energy release rate that Professor Inácio mentioned and govern or is directly related to the critical stretch or critical strain of the bone. Therefore, by using the random field, it's possible to change the random field and simulate another sample, numerical sample of this case. Okay, Here we have the results in terms of global behavior, comparison between load against the deflection. It's possible to see that the peridynamic model has a good agreement between the results with the experimental one. And the dashed blue line is the peridynamic model that we monitoring by using acoustic emission. Therefore, using the acoustic emission data, we analyze the b-value and the natural time for this numerical case. There is no experimental results for this case. Here, the first parameter was the b-value, and it's possible to see that in the beginning of the numerical record, it's possible to see just a few acoustic emission signals, but with low amplitude, and therefore a high value of B is computed. However, very close to the time of the failure of the structure that happens in a sudden way. The b-value, we have a decrease, a very hard decrease of the b-value, indicating therefore the rupture. When we analyze here the natural time, we analyze just the variance of natural time, that is our ordered parameter that is employed to know the criticality of the structure. It's possible to see that close to the normalized time of 0.5, we already, according to the natural time, we already have the criticality, and it's possible to see that this value is very close to its critical value, indicating that after this point, the structure is already in a critical situation. Here we have the comparison between the final configuration of fracture between experimental and numerical results. As I said, when we change the random field, it's possible to simulate different numerical samples, and therefore it's possible to have a statistical analysis and also from the crack path obtained and to compare with the experimental. Based on the results obtained from simulations, acoustic emission proves to be a powerful tool for detecting and analyzing failure mechanisms and structures. The use of simulated acoustic emission data enables to control the investigation of complex scenarios, providing evaluating insight into the damage evolution, and advances in computational modeling, signal analysis techniques, and the numerical methods continue to expand the potential of acoustic emission in research and engineer applications. Thank you so much. And here is my email if you have some questions or to share papers and research. Thank you.
Thank you very much, Leandro. Well, now I killed the schedule, but there are some question or commentary, please. Okay, in key. Very interesting talk. Thank you. How do you define entropy in this system? You reply, Leandro.
Yes. Basically, this entropy is computed by using the just a second here, by using the energy of that characterize the event that could be in terms of acoustic emission contest, the amplitude of the acoustic emission event, or could be a good feature of the acoustic emission signal, such as, for example, duration, rise time, or another parameter. And the specific equation to compute the entropy could be found here in the Varotsu's book. That is not so complicated, and it's very similar to Shannon entropy, that it's another kind of entropy, but is also employing ordering to know the disorder of the system.
Thank you.
One question.
More question. Okay.
Okay, thank you.
Okay, thank you very much. And now, please, Professor Giuseppe, if you like to speak a few words
Yes.
in the.
My compliments to Leandro and also for you for your very interesting presentations
Thank you.
related to numerical
Thank you,
models
Joseph.
and acoustic emission. Probably it's very difficult to understand for the first time if you hear a presentation from Leandro and also from Ignacio. But I know that are very powerful. No, but I've read some words that I can show also to the people that is hearing now our webinar. Therefore, these are my webinar concluding remarks. Thank you for joining today's insightful webinar on the interaction between numerical strategies and experiment tests in acoustic emission techniques. I began with a presentation focused on the application of acoustic emission and other non-destructive techniques to real-world challenges, such as the case of the Garisenda Tower. Next, Professor Ferenc Kuhn discussed the fiber bundle methods, demonstrating how this numerical tool enhances also by acoustic emission the understanding of the progression of material damage. Finally, Professor Leandro Friedrich and Professor Ignacio Turrios explored the application of discrete numerical and peridynamic strategies in simulating acoustic emission tests in structural contests, emphasizing their potential to deepen our understanding of damage processes. As we conclude, I encourage you to reflect on these insights shared today. The collaboration between experimental techniques and numerical simulation is vital for advancing our understanding of materials under stress. We hope this webinar inspires you to further explore this methodology in your work. Thank you once again for your participation, and we look forward to seeing you at future events. Before to conclude, do not forget to submit your work on this topic to the special issue, Advanced in Acoustic Emission Techniques, Test Interpretation, and Numerical Simulation. Have a great day.
I would like to thank to our chairs and speakers for your time and interesting contributions to this topic. I'd also like to thank to our participants. I hope you find this webinar both interesting and insightful. Please note that certificates of attendance are available for all registered participants on your Sci4 dashboard. As a reminder, the recording of the webinar will be made available as soon as possible on the webinar webpage. I wish everyone a nice day. Bye-bye.